Okay, so we're up and running. That's enough about my feelings on candidacy and qualifying. So the midterm is made, right? So that means you can ask any questions without fear that what you ask is going to alter what's on the exam. Right? And then I have some questions, some previous questions. So would you like me to run through a couple examples of what has been on the previous before you guys ask questions, or do you want to do it the other way around?
I guess go through the previous.
Okay, so so it's a little out of order. I've changed the ordering, so I've got to look at both final and midterms. Okay, so some examples for short answers. Right, ones that don't involve calculations. So here, right? So I'll give you a strain like this, small. I specifically say that it's a elastic infinitesimal strain tensor, right? And then I ask to sketch the faces of a cube, of a unit cube, before and after deformation, right? So what's the worst thing you can try and do on this?
Do any kind of calculation?
Well, yeah. So so this should be like a 20-second draw. Right? Don't try and draw the whole 3D cube. Right? You're going to draw a cube to some distorted rhombohedral. Right? I mean, like it's not going to. Right? It's shearing in 2 directions and it's stretching in 3 directions, right? So it's not a easy 3D thing to draw. Just draw the 3 faces, right? And you can treat this 3D problem as 3 2D problems, right? Right? So if you look at the XZ face, right? So we initially start as a cube, right? And so we want this to be, all right, so this is Z, this is X. Okay? Make sure we keep a right-handed coordinate frame, right? And if this is 1 and 1, well, what are we doing? We're stretching in X, right? So we're stretching in X. What does our 2D What does our 2D strain tensor, XZ strain tensor look like?
5, 1, and then 1, 4.
Right? 5, 1, 1, 4. Right? So here we're stretching in X, we're stretching in Z, right? By roughly equal amounts, right? And then we're shearing in the positive XZ direction. Right? So now we have this stretched cube that we're now shearing. Right? And we have something that looks like this. Right? And then obviously my angles and stuff aren't great here, right? But right? That's the kind of.
So you want us to draw the angles?
Well, yeah, I mean, right, here, in this case, I can tell this was supposed to be stretched by 5 and 4 times 10 to the minus 3,
yeah,
and sheared by 1 times 10 to the minus 3, but my shear here is exaggerated just because I wanted to show.
Yeah.
Right. So either draw it a little closer to scale or make a note, right, that says shear angle is exaggerated.
Yeah.
Right.
Okay.
Right. Right. So something like that, right? And these are the sorts of short answer, right? So I'm expecting a couple of these to take you like roughly 20 minutes, right? So I'll have times on the exam, right? Say, you know, I'm anticipating this section taking 20 minutes, right? I'm anticipating this taking 40 minutes or whatever, right? So think about that, right? Because if you take 40 minutes on the short answers, right, that doesn't leave you a lot of time for that.
So is that question on the previous midterm?
This was a previous exam question.
So could you please upload the midterm on the Khan, because
I can't do that because there are one or two parts of questions that are being reused, right? Not whole questions, right? But little bits. So unfortunately, I can't. That's why I'm going through examples of what the questions are going to be kind of like. So another one, right? So a schematic plot of entropy and internal energy, right, as a function of elastic strain, right, for a crystal and an ideal elastomer. Right? So what does internal energy versus strain for an elastomer look like?
It's not changing.
It's constant, right? What about entropy?
Increasing.
Increases, right? Is the curvature concave up or concave down?
entropy decreases it when it stretches.
Concave.
Yeah, so just think about it, right? It's decreasing, right? But how is it decreasing? Right? Right, and then what about for a crystal?
Crystal U will increase.
Increase, right? And the entropy?
Entropy will decrease.
Right,
It's gonna
constant.
increase.
Constant.
Right? This is idealized, right?
Okay.
Right? You're not. Are you changing any configuration when you elastically stretch a crystal? No.
Oh yeah.
Right?
Elastic.
Right? So again, 30 seconds if you know it, right? If you don't know it, think about it for a long time.
Not too long.
Right? There's a chance for a mathematical question. Right? So the short answers, and this one I asked for a combination of 50 points, right? So there were 7 questions, you only had to answer 5 of them, right? So one of them for the more mathematically bent, right? I said, I noticed I didn't ask for a proof of this, right? Because that would be a little different, right? I said provide an argument that any stress tensor with 0 trace can be transformed to a stress that represents a state of pure shear, right? So that means if I have a stress tensor 3 minus 2 minus 1 something arbitrary, right? That there is some reference frame that this is
Pure shear.
pure shear, right? Pure shear meaning no normal components, right? So 0 on the diagonal, right? And so,
Is that a 4 or 11?
oh, I guess that's a 4.
Okay. I was just curious.
As long as it's symmetric. Right?
Symmetry.
I
Yeah.
just made something up.
All right. Cool.
Unfortunately, this pen is not good at finding detail. Right. So how can you think about this?
Hydrostatic and deviatory.
Right. You can get hydrostatic and the deviatoric part. Right. The trace is always an invariant. Right. So there's multiple ways you can attack this. Right. You could also easily find the coordinate transformation that does that. Right? Of course, with this one, it would be a little difficult. On the exam, I would give you something that looks more like this, right? That can be done analytically on paper without real difficulty. Right? But yeah, you don't have to offer. This is not a proof, right? I'm not saying formal, right? It's provide an argument, right? So that means you can discuss it conceptually in words. Provide a physical mechanism which explains why slip lines are often straight in FCC metals with low stacking fault and wavy in FCC metals with high stacking fault. Right? And it's just partial dislocation, right? Low stacking fault means extended partials difficult to cross slip. Right? Whereas high stacking fault, partials, if they exist, are close together. Right? They can come together really easy to cross slip. And there's some things like that are right from the reading. Briefly explain Neumann's principle and how tensor symmetries must be related to crystal symmetries. Right? A couple sentences. Right? Right, so sketch the bond energy curve for a material with high elastic modulus and a weak elastic modulus. Discuss the relationship between elastic modulus and the shape of the curve, and describe the relationship between melting temperature and elastic modulus. Right. Describe the relationship with chiral stress and with the core structure of the dislocation. Right? And that, I mean with. Right? So very similar to the quiz question that I asked. Right. Describe the relationship between dislocation density and yield stress in a single phase material. Right? So that immediately tells you, right, ignore all particle stuff. Right? It's a single phase. Right? And yield stress, meaning what's that? Yeah, right. So we're just talking about dislocation relationships, right? So that's Taylor hardening, right? Square root rho. Right? Where does square root rho come from? Okay. So that's short answers, right? That's going to be roughly 20 minutes, right? So some examples of problems, and I will post these problems because I'm not reusing them, right? So I'll post a couple of these, so don't feel that you have to scramble to write these down. Okay, so an example. Here we've got, this is a reference frame, X and Y. Here, this is a piece of a single crystal silicon wafer. All right, and we want to make some kind of microelectronic sensor. All right, so we're going to grow metallic strips. So single crystal, growing them on this wafer. All right, so we're growing them like this, where the angle is 40 degrees with respect to the y-axis, right? And the crystal has the orientation where the 100 crystal direction is parallel with the long axis of the strip, and the 010 is normal to the silicon surface, right? So the silicon metal interface has an orthogonal direction 010, right? So the cube directions of the cube faces of the single crystal. And then I give some design components, right? So that under the stress, right, which I'll give in a minute, right, fibers can't have any normal strain greater than 0.1% or shear strains greater than 0.01% or they'll debond, right? So I give you some, right, so the strain has to be less than or equal to 0.1% normal, right? So which means sigma xx or sigma yy, I mean epsilon, and epsilon yz has to be less than 0.01%. Right? And then I give a stress tensor. Okay, so you're designing a cylindrical pressure vessel, take 2. And so you've got basically a state of 2D stress. Right, you've got a hoop stress and an axial stress. I don't don't expect anyone to remember the equations for the stress, right, in a pressure vessel, right? You may or may not have seen them in the past, but so I give you the form that relates So it's a 2D stress state, right? The hoop stress is the pressure times the radius of the vessel divided by the thickness of the, right? These are for thin walls, right? So the thickness is small compared to the radius, right? Okay, so it's a 2D stress state. So is the strain 2D or 3D? 3D, right? So that's the first important thing to remember, right? That there's Poisson effects, right? You have to think about the right, the thin, right? That as you stretch it, the wall's going to get thinner. Okay, so your design task here is you want to design a alarm which triggers when some overpressure condition exists, right? And you're doing that with our old friend, the strain rosette gauge, right? So we've got our 3 strain gauges. Arrayed something like this.
They're arrayed off of one axis, or?
What's that?
I'm sorry, I don't understand the drawing.
Oh, this is the axial. And right, you're putting this on the surface of the.
Got it.
Okay. And you have a the limit is the maximum pressure that this vessel can handle is 2 pascals, or 2 MPa. 2 pascals would not be very right. And right, that's the design. I give you a Young's modulus of 200 MPa and a Poisson's ratio of 0.3. And I basically ask, determine the max allowed stretches on each of these rosette gauges that correspond to the strain at the critical pressure, right?
So the critical pressure is 2 megapascals.
2 megapascals, right? So from that you compute the stress, right? You use your isotropic elasticity equations to get the strains, right? You get a strain tensor.
Are we also given a radius and thickness in this?
Yeah, you get the complete geometry of this.
Just making sure it's matching.
Yeah. Well, even if you weren't, you could calculate it in terms of radius and thickness, but that's a pain in the ass. Right? But you could do it. Right, so you compute the stress. From that, you compute the strain using your isotropic elasticity equations, and then it's a matter of doing the coordinate transformations to compute this. Okay, so how many do you actually have to do? Well, okay, so this gauge is already aligned with the hoop, right? You don't have to.
So you just do 30 degrees.
In fact, you only have to do one of these, right? It's isotropic, right? So these are symmetric with each other, right? So you can completely ignore this one, and you only have to do one of these gauges, right? So the important thing is, again, look at the geometry of the problem, right? You have to remember it is a the strain tensor is in fact 3D, right? Because it's have Poisson effects. And so I broke it up. That first question was worth 20 points. This one was worth 25 points. And then I gave and then the third question that was worth 15 points. I basically said, you have a positive screw dislocation, right? And we know that the ZX component of stress is given by this, right? And we also know that sigma ZX equals sigma XZ and sigma ZY equals sigma YZ from symmetry. And so then I asked so use the stress equilibrium to write sigma YZ as a function of sigma ZX. Right? All right, and then use this relationship to actually come up with ZY, right? Now, of course, it's open book, right? So you have the final form for what ZY should look like, right? So it's just a matter of working through it from the stress equilibrium, right, that you've gone through, right? Then to just plug that in and work the algebra out to get to the answer that you know. I like dislocation questions like that, right? Another one that I used. Oh, so that polymer bulk question that I asked, the stretch, that was an exam question that I used. So
The nylon bolt.
the nylon bolt.
Okay.
Right, that was an exam question. Right. Another dislocation question. Right, I said consider two perpendicular screw dislocations. Right. Right, separated by some distance. And I had to make a correction to this because, yeah. So I said two parallel screw dislocations, one with Z, one with X, parallel with Z, one with X, and I say, calculate the total force on the second dislocation is given by this, right? So that's the force. Right? So I specifically say that total force, right? So how do you, right? So you would plug this into the Pech-Kohler equation, right? That would give you force as a function of position, right? So then you find the total force by integrating along the line length from negative infinity to positive infinity. Right? And then I say, and then for part B, I say compute the total moment acting on the dislocation. Right? And say do the dislocations remain straight? Will they, right? Right. So you can see here, right, you'll end up with a torque. Right? And so that torque is going to want to cause the dislocations to rotate relative to each other so they're not aligned at 90 degrees. Right? So you'll end up with dislocations that want to twist like that. Right? But this end here that doesn't see any force or moment doesn't want to move. Right? So the whole dislocation wants to rotate to become parallel, but it can't do that because, right. And so, yeah, that was another 25 point kind of thing. Right, and so you'll get 3 of these, right? I'll say do 2, right? And then you can decide, right, how many points you want to go for, right? Because they're not all quite exactly the same. But in this case, the exam was worth 120 points, but I graded it out of 100. Right? So if you pick the 2 most difficult questions, right, and you did the max number of short answers, right, you could have had a possible 120 points. Or you could have picked a harder question, an easier question, and only have tried for 115 points, right? But it was still graded out of 100. Right? So there's always extra points built in, but you might get some extra points for trying more difficult. So let's see. Some more on this other exam. Some more short answer questions. Right. Sketch the time-dependent creep and recovery behavior for the Kelvin-Voigt model and the Maxwell model. Right. Briefly discuss the main mechanisms which contribute to particle strengthening for both cutting and ripping. Right. Right. Which means when I say briefly discuss, I mean one sentence for a mechanism. Right? This is the short answer. You don't have time to give me a paragraph. Right? What are the mechanisms in one sentence? Right? So it's chemical strengthening. It's the creation of new surface energy when you shear through new surface area when you shear through a particle. Right? It's going to be proportional to the surface energy. Right? Antiphase boundary. Right? It's going to be proportional to the area of the surface. Right, the cross-sectional area of the particle, right, and the APB energy of the, right, real short one-line things is what we're looking for. Solid solution strengthening, right. Consider an edge dislocation, right. Sketch the interaction energy versus position of the edge the edge dislocation encounters atoms which are stiffer and more compliant than the matrix. Right. Quick things like that. So I'll put up the calculation type question. So this one, the problems were take home, so they're a little more difficult. But I'll give you the problem anyway because I liked the idea of it, but realized that this was on the take-home exam, so you could not. There wouldn't be time for me to ask this exact question. So we said we have a nickel alloy, right? And we want to make a solid solution strengthened alloy with it. And so I point out that palladium and tungsten have almost exactly the same atomic radius, right? And that palladium and copper have almost exactly the same elastic modulus. So if we assume that nickel and palladium form a solution, I say calculate the solid solution strengthening for palladium. And then I say use the discussion in the book and example 5.2 in Courtney, right, to draw conclusions on the relative effect of modulus versus misfit for solid solution strengthening in FCC. Keeping, in fact, right, so the reason why you can do this problem is because I've got examples where both are the same, right? So because palladium and copper have the same modulus, but different sizes, right? I can keep the one constant and compare how keeping one constant and changing the radius affects it, and then I can have an example where I can keep the radius constant and change the modulus, right? And see which is going to give a proportionally bigger change, right? But this one's a little too in depth for in class, right? So that's why it works as a take-home problem, but not in class. Okay, so we've got a couple minutes, so let me take any questions you guys have. I'll post the long answers that we went over, right? And don't spend a huge amount of time memorizing them. Like, work through them. The real benefit from that is working through them and seeing the shortcuts, right? The fact that I set up the geometry where you don't have to do all the work, right? If you find yourself doing all the work on the exam, it means you're missing something, right? The first one, right? The crystal symmetry allowed you to turn it from a 3D problem into a 2D problem. All right, and the second one, the fact that it was isotropic and the symmetry of the strain rosette, right, meant you can cut out 2/3 of the work. That's where and just thinking about the questions, right, and then the nylon bolt question, right? So the long answers are more applied kinds of questions, right? And they usually have two concepts in them, right? So the first one I'm asking about coordinate transformations, right? And about anisotropic elasticity, right? In the second one, I was asking about isotropic elasticity, but also about coordinate transformations and inverting stiffness and compliance. Right? Okay, so questions. It will be 1 hour. Right. Chances are, based on my track record, even I'll try my best to make it a 1 hour exam. Probably a chunk won't finish in 1 hour, right? And that's okay because grades are not right. Just think historically, you've heard a lot of things about classes, right? Bad and good, and you probably haven't heard many people complaining about the grade that they earned in this class. You may have heard people complain about lots of other things about this class, but hopefully the grade they earned is not one of them. So try not to panic too much, right? If you feel your performance on the exam was not good, it's relative to everyone else's crappy performance, right? And my inability to make the test. That there's a disconnect, right, between what I think the level is and how you guys perceive the level. I haven't figured out how to align those things. So. Was this useful or disheartening? Do people feel better about the exam or worse? I'm sorry. I'd rather shock you now than shock you on Monday. The point of the exam isn't to try and be a jerk. We're trying to make passes. You know, to be honest, I really look at the exam more as a feedback on my teaching ability rather than your performance ability, right? And I think that's how exams really should be, right? It's an evaluation as to, am I getting the ideas that I think are important across? Right? It doesn't make it any easier on you guys, right? But I'm not trying to make it. I have no motive other than that. Okay. Well, we used up the whole time. So, have a good weekend, and we'll see you on Monday.